The next type of conservation of momentum problem is going to involve collisions. And this is where we're going to have things that are apart and they come together and collide, bang into each other. And there's two types of collisions, and this is pretty informal. There are sticky collisions. Later on we'll call these inelastic, but for now we're just going to call them sticky collisions. And that's where two things or more, but generally we're going to think two things come together and then they stick together and then they go moving off as, stuck together as a single unit. The other one you can probably guess would be these two things come together and then they bounce apart from each other and they go off in their respective directions. So that would be a bouncy collision. And later on, we'll start talking about at least some of these bouncy collisions will be considered elastic, but we need to get into chapter 10 on energy before we can really talk about that more precisely. So now here, let's look at our example of a sticky collision. We have an astronaut. She's in space, deep, deep space, so we don't have to worry about any external forces. There's no gravity force, etc., acting on her. She's not moving relative to a local frame of reference, and her mass is 100 kilograms. We have a cargo box coming at her directly. It's moving towards her at 2 meters per second, and the mass of the box is 50 kilograms. She's going to catch the box, and they are both going to end up going to our left. And I want to predict what is the speed. What will be the speed? So let me just make a mark of that. So what is post-collision speed of our astronaut? Okay, so as with all conservation momentum problems, we have to think about what would be an appropriate system. We definitely are going to include the astronaut because she's the main part of our question, but if I were to include just her, then her interaction with this box would be an external event. There would be external forces. Her momentum will change. We cannot say that momentum is conserved. However, if I think about including the box as well as the astronaut, then any forces they exert on each other in the course of her catching the box, she'll push on the box will push on her. Those are internal forces. And internal forces do not change the overall momentum of the system. So that's going to be our approach. So we can say that momentum will be conserved for our astronaut box system. Let's go ahead and label 1. The object says 1 and 2. I'm going to call the astronaut 1, and I'm going to say the box is number 2. Then, for any kind of two-body momentum problem, conservation momentum problem, I just begin to say, this is what I write out. First I say momentum's conserved. Well, what does that mean to say? It means whatever momentum our system had before the event, in this case the collision, and that's reflected here, these two. This is the momentum of the astronaut. This is the momentum of the box before the collision. Is going to equal the momentum, the momentum of the system after, and that's going to be m1 v1 prime plus m2 v2 prime, and that's going to be the momentum after the collision. Now I want to customize this basic work for any type of problem statement to our particular situation. So I notice that our astronaut's not moving, so that means her momentum is going to be 0. Now on the right side, I want to think about, really what I want to know is I want to know what her speed is going to be after the collision. But let's think about that. If you catch a box and you maintain hold of it, then the speed of the box, the velocity of the box is going to be exactly the same as your velocity. So really, there isn't a separate v1 prime and a v2 prime. So what we're going to say is, since v1 prime is going to equal v2 prime, we're just going to use v prime to represent the velocity of both the astronaut and the box. So I'm going to rewrite this. I'm going to come down and say, okay, here's m2v2. That's the momentum of the box before. And what I have here is I've got m1v prime now plus m2v prime. Okay, because if I kept it as v1 and v2 as separate, that'd be too many unknowns, right? So I avoid that by saying, look, they've got the same velocity. All right. So now we keep coming and we're going to basically pull out the v prime. So I've got m1 plus m2. Factor out the v prime, I guess, is what you would say. And I realized, okay, the physics is actually done now because that's what I'm after and I know everything else. So let's rearrange to solve for v prime. And we're going to get m2 v2 all divided by m1 plus m2. And I like to write that as a ratio of the mass. So that's m2 is the total mass in motion before the collision. Then after the collision, we have both the astronaut's mass and the box's mass moving. And then we have our original velocity of the box. So we can see that since there's more mass moving after the collision than there was before the collision, v prime should be and will be a smaller value. And that's going to, hopefully that makes sense to you. Because the combined mass, let's just say it makes sense to you, because I want to wrap this up. V prime then, put in the numbers. What was the mass of the cargo box? I think it was 50. Let's just double check real quick. 50 and 100. All right, so there's 50 kilograms. Then the total mass underneath, the combined mass of both the astronaut and the box is 150, 100 plus 50. And the initial velocity of the box was 2 meters per second. And so we can see it's going to be 1/3 of 2 meters per second. And I don't want to get out calculator, so... Oh my goodness, I'm drawing a break. I think I can get this. Okay, 1/3 of 2 meters per second. All right, I see it now, 0.67 meters per second. But, wait a second. Is that going to be positive or negative? I need to clean this up. I forgot to include a frame of reference. Well, I'm going to go ahead and make to the left positive for my frame of reference. Which means then everything, I don't have to add a negative sign because to the left is positive. So that is the velocity of the combined astronaut and box system. Bye.